Okay, we're going to finish up talking about net force now. We talked earlier about how a net force can cause an object to accelerate. In other words, it can cause an object's velocity to change. I kind of say that this is just, before physics, you would describe this as a change in the object's motion. Well, there are an infinite number of net forces that can be put on an object because there's an infinite number of magnitudes of the net force. You could have a net force as small as just being barely over zero. You could have a net force that is practically as big as, well, as big as you can get. What is going to control how much the object on which the net force is placed, how much its motion changes? The answer to that is the object's mass. And mass is simply the amount of matter contained in an object. The amount of matter contained in an object. Now, you probably saw this when you did the lab earlier, but let's go back to the simulation one more time. Right now, we have this little robot thing pushing an object of 50 kilograms. If I apply a force of, let's do the maximum force. 500 newtons. Oh, I guess I got to hold it out there. 500 newtons. Look how quickly that speed changes, okay? It accelerates at a great rate. Let's reset this. Let's check all of our boxes again. Now let's put some more mass on there. Let's make him push the refrigerator too. Notice how quickly the speed is changing this time. The increased amount of mass means that the speed does not change at as great of a rate. So the bigger the mass is, the smaller the acceleration is. We can still get up to the same speeds. We can still get to the same velocities, but it's just taking a lot longer to do so. The acceleration is simply smaller. Okay, so we see that mass affects how much an object accelerates, okay, how much the motion changes. Because that's really what acceleration is. It's a measure of how much an object's motion changes in a given amount of time. And mass is simply the amount of matter contained in an object. At this point, I have to give you a warning. Do not say that mass is how much something weighs. How much something weighs is its weight, and weight and mass are not the same thing, as we will see in the next 2 weeks or so. They are completely different. One depends on the other, that is true, but they are completely independent quantities. Do not say weight when you mean mass, and do not say mass when you mean weight. What happens is that objects with mass have this property where they resist any changes to their motion. Okay? They just have this innate property. Anything with mass, anything, could be something with very little mass, something with a lot of mass. They resist changes to their motion. Objects with mass resist accelerating. They don't want to do it unless something makes them. Okay? This is why Newton's first law works. Objects with mass, or objects that have mass and are at rest, just aren't going to stop moving unless an outside net force acts on them. Okay? Objects don't just start moving and accelerating for no reason. A net force has to act on them. Objects that have mass and are moving don't suddenly stop. I think the first part of that, objects that have mass and are at rest don't suddenly start moving, that makes sense. You've never seen that happen. Some force has to come along and act on the object. What doesn't make sense to a lot of people is that objects that have mass and are moving, they don't just stop unless an outside net force acts on them as well. This is very confusing to people because in our experience, things typically stop moving after a while. But there's a reason for that. The reason is a net force is placed on it, on that object, whether or not you can see it. Most of the time, it's due to air resistance or friction. And that's not necessarily something that you would expect if you didn't know that those things existed. Okay? Objects that have mass and are moving do not just suddenly stop. They stop because there's a net force placed on them. The larger the mass, the more it resists a net force. And the less the motion changes. The larger the mass, the more it resists a net force, and the less the motion changes. That's why in the example we just saw in the simulation, when the robot was pushing the 50 kilogram box, it was very easy to change the motion very rapidly. Once the refrigerator got put on top, it was much harder to change that motion. Let me give you another example. You have two objects, a baby stroller and a broken down car. You can apply the same force to each object for the same amount of time. Which object will change its motion or accelerate faster or at a greater rate, and why? You're pushing them at the same rate, or with the same force for the same amount of time. It's pretty obvious. Even if you push with the same force, the baby stroller is going to accelerate at a greater rate. It's going to change its motion faster, change its velocity. Why is that? Because it has less mass. So this idea that more mass means it's harder to change the motion is called an object having inertia. I-N-E-R-T-I-A. This is a key word to know. It's the concept. It's not the same. Inertia and mass are not synonyms, but objects with mass have inertia, and they're directly proportional to one another. The amount of inertia something has is only based on the amount of mass an object has. More mass, more inertia. The more mass something has, the more it resists changes to its motion. So an inertia is not a force, by the way. It is simply a concept that we have come up with to explain why objects with mass, with more mass, do not accelerate at the same rate as objects with smaller mass. Okay, it has to do with inertia. Objects with mass do not, they resist changes to their motion. I mean, there's a whole bunch of other ways I can say it, but in the interest of time, we'll just leave it at that. Inertia is an object's inherent resistance to changes in its motion, to accelerating. The more mass something has, the more inertia it has. Okay? More mass, more inertia. Now, I want you to put stars around both this and the one above. It's key to remember both of those. Matter of fact, on some of your homeworks, there will be questions that strictly say, here's a bunch of objects with different masses, which one has the most inertia? It's extremely easy. You're simply looking for the one with the most mass. As soon as you find that, boom, question's over. We're going to finish this set of video notes with a bunch of examples, just common examples that you'll see where we reason out using things like equilibrium and mass and inertia and net force, how the answers to these problems. So, net force problem number 1. An object has only one force acting on it. Is the object necessarily in equilibrium? And in order to answer this one, I'm actually going to go back to a different simulation that you looked at, the tug-of-war simulation, right here. Now, if there's only one force acting on the cart, okay, I need to put a person on either the left side or the right side. No matter where I put them, oh, I gotta hit go, that's right. No matter where I put them, it doesn't matter. I'm still going to get some acceleration if there's only one force acting on it. So look, I only have a leftward force. Let's return this. Doesn't matter where I put them. Can I put these guys over here? Nope, I can only put these guys on the left. I must have an acceleration if that's the case. I know I have an acceleration because that speed is increasing. Okay? So if there is only one force acting on an object, then that object must be accelerating. In other words, if it's accelerating, it cannot be in equilibrium. The reason it can't be in equilibrium is because if there's only one force, that has to point in a certain direction. If we wanted balanced forces, we'd have to have at least one other force pointing in the opposite direction to balance them out. So there is no force to balance out the one force that is acting on the object. Okay? So an object with just one force on it, which is relatively rare, okay? Projectile motion and free fall are actually examples of times when objects only have one force on them, and think about that. Those objects are always accelerating in some direction. An object with one force on it cannot be in equilibrium. It must be accelerating, okay? It must have its must have a changing velocity. On the other hand, what about an object with two forces acting on it? Is that object necessarily in equilibrium? Again, let's go back to that simulation. You might think, yeah, if there's two forces, then they must balance out. Well, what if we did this? Okay? If I have two forces on there, I have a left force and a right force. But look at that. There's still some acceleration because that speed is going up and up and up. Okay, the motion is changing. The only way, if I have two forces, to get there to be no acceleration is if those forces are exactly the same. So an object has two forces acting on it. Is the object necessarily in equilibrium? Not unless the forces are exactly equal in magnitude, equal in size, and opposite in direction. Because think about it, even if they're just equal in magnitude, they also have to be opposite in direction for there to be no net force. If there were two forces in not exactly the opposite direction, there would still be acceleration in some direction. Let's move on to the next. If two equal forces are applied to an object, what should the angle between the two forces be so that the net force is as large as possible? In other words, for this question, think about you're trying to push a truck or something. You're trying to push a car that's broken down. How do you want to angle your force between you and whoever's helping you so that the car, so that the maximum force is on the car, so that you're not working against each other, so that you're getting the car the biggest acceleration possible? It's pretty obvious if you think about it that way. What you want is two forces in exactly the same direction, like so. And what would we say is the angle between those forces? That would be 0 degrees. What happens if you have two forces at 0 degrees apart from each other is that means they're in the same direction. If they're two equal forces, then your forces will add like this. The net force equals F plus F, and it's simply 2F. Both of your forces are in the same direction. Okay, great. So if you want the biggest possible net force on an object, you only have two forces to deal with, you want them to be in the same direction. What if we wanted the opposite? What if we wanted two equal forces applied to an object and we wanted the net force to be as small as possible? So imagine you don't want something to accelerate at all if you can help it, or be as small as possible. You have two equal forces. Well, again, the obvious answer is you want, let's say, one force pointing to the right, or one force up, or however you want to write it, and the other force to the left. Okay? What's the angle between these two forces? 180 degrees. The forces balance. And they kind of cancel each other out. Uh-oh. All right, let's look for another pen real quick. All right, technical difficulties. Let me go find something that works to write with. Okay, this will work for now. Cancel each other out. In other words, if you were writing the net force here, you would have, let's say, a force of F, and the other force of F is in the opposite direction. It would be like F minus F. And what would that give you? A net force of 0 newtons. Okay? So if you want the net force to be as small as possible, and you have two equal forces, you got to make sure they're in opposite directions. All right. A book sits motionless on a coffee table. The force of gravity on the book is 10 newtons, as is the force from the coffee table on the book. This is known as the normal force. We'll talk about that a little bit more later on. What is the net force on this book, and is it in equilibrium? If you can't answer a forces question by using one simple equation, or and you're kind of thinking you might have to do some math here, your best bet is to start with a free body diagram. Okay, if you can't answer it by just writing down one equation and then solving it like you did in the kinematics unit, you have to draw a free body diagram, and then you have to write net force equations. So that's what it's looking like I'm going to have to do here. Okay, here's my object. It's a book. Here's my axis. Force of gravity on the book from the earth pulls it down. Force from the table points up. Okay, the force on the book from the table. In the x direction, there are no forces, so I know that's in equilibrium in that direction, so the net force is 0 newtons. In the y direction, we have the positive force in the positive direction is the force from the table, minus, because it's in the negative y direction, the force of gravity. Okay, it doesn't mean that the force of gravity is some weird force that's always negative. It just happens to be in the negative direction here. I can plug in the numbers. Force of gravity on the book is 10 newtons, as is the force from the coffee table on the book. So we have 10 newtons minus 10 newtons is 0 newtons. So the net force on this object in both directions is 0 newtons. Is it in equilibrium? It is. It is in equilibrium. And I don't want you thinking that every object is in equilibrium. All of our examples so far, the object's been in equilibrium. That is not always going to be the case. Wait till we get down to our last example. An object is speeding up. What do you know about the net force on that object? I'm not asking about direction, okay, necessarily. I'm just saying I guess we could know about direction. If an object is speeding up, that means that its velocity is not constant. It is accelerating. And if the object is accelerating, then that means that the net force is not 0. So since it's accelerating, F net is not 0 newtons. Now, on the flip side, if an object has constant velocity, what do you know about the net force on that object? Constant velocity means no acceleration, because acceleration is the change in velocity over time. If there's no change in velocity, there is no acceleration. That's key, by the way. Saying that there is no change in velocity means no acceleration. Just saying there's no velocity does not mean no acceleration. Acceleration is the change in velocity over time. You have to understand it's not just velocity over time. It is the change in velocity, delta V. Delta meaning change in, V meaning velocity, is the change in velocity over time. Look at that reference table. It's spelled out right there for you. So since there is no acceleration because the velocity is constant, so F net is 0 newtons. Okay? Our last question, and this will bring us more into questions that you will start to see from here on out. An object has a force, or has two forces on it. One force is in the positive x direction and has a magnitude of 50 newtons. The other force is in the negative x direction and has a magnitude of 30 newtons. Describe the motion of this object. Okay? So here's what we're going to do. This is not something that we can just assume is either moving or not moving, or accelerating or not accelerating. We need to draw a free body diagram. It's not something that's just answerable with one quick equation from the reference tables. So we have our dot. We're just going to label it object. We're going to write our axis. X, Y, those are the positive directions. One force is in the positive x direction. That's to the right here. Has a magnitude of 50 newtons. I'm going to call that F1. The other force is in the negative x direction. Has a magnitude of 30 newtons. We're going to call that F2. Do not label forces with their magnitudes. We can plug those in later on. Give them variable names like F1, F2, or FG, or FF for force of friction, okay? We don't know whether this is the force of gravity or whatever. We're just calling it F1 and F2. That's totally fine here, okay? If you know exactly what the force is, though, you want to name it something that actually makes sense. So, the net force equation in the x direction would be F1 in the positive x direction, F2 is in the negative x direction, so it's going to be minus F2. F1 has a magnitude of 50 newtons. F2 has a magnitude of 30 newtons, so it's minus 30 N, equals 20 newtons as the net force in the x direction. Now, what does this mean? The motion of this object. Obviously, in the y direction, there is no net force. The net force is 0, so there's no acceleration in that direction. Since there is a non-zero net force in the x direction, that means the object is accelerating in the x direction, specifically the positive x direction, because our net force is positive, and that means that the velocity is changing. Okay? F net x is not 0 newtons, so the object is accelerating in the positive x direction. In other words, the velocity is changing as it moves. Okay? So, the key here is net force can tell us about any acceleration that the object might have. And acceleration tells us that the velocity is either changing or not changing. Acceleration of 0 means that the velocity is not changing. Acceleration of that is anything but 0 means that the velocity is changing. And again, if there is a net force, there is an acceleration. If the net force is 0, then the acceleration is 0. Okay? So we've worked through a lot of stuff with net force. We're going to cut it off there. When we come back, I believe we're talking about Newton's second law. This was the first. We talked briefly about the first one in the last video. So we're going to keep moving with forces. All right. This is crucial foundational stuff for not only this unit, but for some other stuff throughout the year. So it's very important that you pay close attention to these videos. Okay? Let me know if you have any questions. I'll talk to you later.